Learjet 40/45 air conditioning system. Architecture Block 1. The air conditioning system on the Learjet 40 and Learjet 45 uses engine bleed air or APU bleed air when installed to provide conditioned air for the cockpit and cabin. This conditioned air is also used as part of the aircraft pressurization and ventilation systems. Bleed air enters the system through the pack bi-level pressure regulating shutoff valve, commonly referred to as the PRSOV. The PRSOV regulates the pressure of the bleed air entering the environmental control system. Under normal operation, the system operates at approximately 18 pounds per square inch. When the HI flow mode is selected, the system increases pack inlet pressure to approximately 26 pounds per square inch, allowing greater airflow through the system and increased cooling capacity. After passing through the PRSOV, bleed air enters the Environmental Control Unit, commonly called the ECU or PAC, located in the aircraft tail cone. The ECU is the core component of the air conditioning system. It contains several major elements responsible for cooling and conditioning the air before it is distributed throughout the aircraft. These components include a pre-cooler, primary and secondary heat exchangers, an air cycle machine or ACM, a water separator, distribution ducting and control valves. The first stage of cooling occurs in the pre-cooler and heat exchangers. These heat exchangers use ram air, which is outside air entering through an air scoop on the top of the tail cone. This ram air flows across the heat exchanger surfaces and removes heat from the engine bleed air. After this initial cooling stage, the air enters the air cycle machine, or ACM. The ACM is a rotating machine consisting of three major components mounted on a common shaft: a compressor, a turbine, and a fan bleed air. First passes through the ACM compressor, where the air pressure increases. The compressed air then flows through the secondary heat exchanger, where it is cooled again by ram air. After this additional cooling stage, the air expands rapidly through the ACM turbine. This expansion produces a significant temperature drop. As a result, the air exiting the turbine becomes extremely cold, approaching near freezing temperatures. This cooling process is known as air cycle refrigeration, which is the fundamental principle used in most jet aircraft environmental control systems. Once the air leaves the turbine, it passes through a water separator. The water separator removes moisture from the air before it is delivered to the aircraft distribution system. Moisture removed from the airflow is collected and then discharged overboard through a spray aspirator system. Removing moisture prevents condensation in the air distribution ducts and improves overall system efficiency. At this point, the air is cold and dry, but it is usually too cold for direct cabin use. Therefore, the system mixes controlled amounts of hot bleed air with the cooled air before it is distributed to the cockpit and cabin. This mixing process allows the system to achieve the desired cabin temperature. In the Learjet 40 and 45, the system provides independent temperature control for two zones: the cockpit, the passenger cabin. Temperature in each zone is controlled through dedicated temperature control valves, which regulate how much hot bleed air is mixed with the cold air from the ECU. These valves are controlled electronically by the Aircraft Environmental Control System temperature controller. In the next block, we will examine how the dual zone temperature control system works. including the integrated ECS controller, temperature sensors, and the automatic and manual temperature control modes. Block 2 dual zone temperature control system and ECS controller. The Learjet 40 and 45 use a dual zone temperature control system, allowing the cockpit and passenger cabin temperatures to be controlled independently. This system mixes hot bleed air with the cold air produced by the environmental control unit, creating the desired temperature before the air is distributed through the aircraft ventilation system. Temperature selection for each zone is accomplished through the environmental control panel located on the co-pilot's instrument panel. 2 temperature selector knobs are provided, one for the cockpit, one for the cabin. These selector knobs command the integrated ECS temperature controller, which is installed in the aircraft tail cone. The integrated ECS controller is a microprocessor-based unit that receives inputs from multiple sensors throughout the environmental control system. Its primary function is to regulate the temperature of the conditioned air entering both the cockpit and cabin. The controller receives input signals from several sensors, including cockpit temperature sensors, cabin temperature sensors, duct temperature sensors, temperature selector positions. Using these inputs, the controller determines how much hot bleed air should be mixed with the cold air produced by the ECU. To achieve this, the system uses temperature control valves. There are 2 primary temperature control valves in the system: a cockpit temperature control valve, a cabin temperature control valve. These valves regulate the amount of hot bleed air that bypasses the cooling process and mixes with the cold air exiting the ECU. The valves are operated pneumatically by engine bleed air servo pressure, but their position is controlled electrically through torque motors. The ECS controller sends commands to these torque motors, which modulate the valves to achieve the selected temperature. If electrical power to the torque motor is lost, servo pressure is removed, and the valve will move to the full cold position, preventing uncontrolled heating. The system can operate in automatic mode or manual mode. In automatic mode, the ECS controller continuously monitors temperature sensor inputs and automatically adjusts the temperature control valves to maintain the selected cockpit and cabin temperatures. When operating normally, the system will maintain temperatures within an approximate range between 60 degrees Fahrenheit and 90 degrees Fahrenheit, depending on the position of the selector knobs. In this mode, the manual temp switch remains blank, indicating that automatic temperature control is active. If the crew selects manual temperature mode, the system logic changes. In manual mode, the cockpit and cabin temperature sensors are removed from the automatic control loop. Temperature control then becomes directly proportional to the position of the selector knobs. The selector knobs now command the temperature control valves directly, allowing the crew to manually regulate the mixture of hot and cold air. Even in manual mode, the system continues to monitor duct temperatures to protect the system from overheating. Another important function of the ECS controller is the low limit temperature protection. A low limit temperature sensor monitors the air temperature leaving the water separator. If the air temperature drops below approximately 37 degrees Fahrenheit, the controller will command the low limit temperature control valve to open. This allows warmer bleed air to bypass the cooling process and mix with the conditioned air, preventing ice formation inside the water separator and associated ducting. This protection ensures that extremely cold air produced by the air cycle machine does not freeze moisture within the system. In addition to controlling cabin comfort, the ECS controller therefore also plays a critical role in system protection and operational stability. In the next block, we will examine air distribution, system indications, and system protections, including pack over temperature protection, duct temperature monitoring, and ECS CAS messages displayed to the flight crew. Block 3: Air distribution, system protection, and CAS messages. After the air has been cooled, dehumidified, and temperature adjusted within the environmental control unit, it is routed to the aircraft air distribution system. This system delivers conditioned air to both the cockpit and the passenger cabin. The air leaving the ECU enters a system of ducts that distributes airflow throughout the aircraft interior. These ducts provide air to the cockpit outlets, the cabin diffusers, and the overhead ventilation outlets. In the cockpit, air is delivered through adjustable directional outlets, often referred to as WEMAC outlets, located above the cockpit area. These outlets allow the flight crew to adjust both airflow direction and volume for individual comfort. In the passenger cabin, conditioned air is distributed through overhead diffusers and floor-level outlets located along both sides of the cabin. The distribution system includes splitter mechanisms that regulate airflow through different ducts. These splitters act as mechanical devices that balance airflow between cabin outlets and floor distribution ducts. The splitters respond to temperature changes within the ducts. As the temperature increases, the ducts expand slightly, allowing the system to adjust airflow distribution to maintain balanced cabin ventilation. In addition to normal distribution, the environmental control system includes protective monitoring systems designed to prevent overheating or abnormal operation. One important protection is the pack overtemperature protection system. A temperature sensor located within the ECU monitors the temperature downstream of the ACM compressor discharge. If the temperature exceeds approximately 450 degrees Fahrenheit, the system will generate an amber CAS message indicating pack OVHT. This condition alerts the crew that pack discharge temperature is excessive and requires corrective action, typically by reducing bleed air temperature or airflow through the system. The system also monitors duct temperatures in both the cockpit and cabin air supply ducts. If duct temperature rises above approximately 300 degrees Fahrenheit, the system generates caution messages: COCKIPT duct, OVHT, or CAB duct, OVHT. These messages indicate that duct temperatures have exceeded safe limits, usually due to a malfunction of the temperature control valve or abnormal system operation. When these conditions occur, the ECS controller commands the associated temperature control valve to close in order to limit hot bleed air entering the duct. Separate temperature limiters provide additional protection. If duct temperature exceeds approximately 210 degrees Fahrenheit, these limiters signal the ECS controller to close the respective temperature control valve, even before an overheat condition occurs. This provides an additional layer of protection for the distribution system. Another CAS message associated with the environmental control system is L or R EMA press, On this message indicates that the emergency pressurization valves for the left or right engine have opened, either automatically or through manual selection. When emergency pressurization is activated, bleed air from the engines is routed directly into the cabin distribution ducts, bypassing the ECU. This provides a rapid source of pressurized air, but does not provide conditioned air cooling. The system also includes the HI flow mode, which increases airflow through the pack. When HI flow is selected, the PRSOV allows higher pressure bleed air into the ECU. This increases airflow through the system and improves cooling capacity. However, this mode increases engine bleed air extraction and can slightly reduce engine performance. For this reason, HI flow should normally remain off during takeoff and landing when using anti-ice, and above 30,000 feet in accordance with aircraft operating limitations. When HI flow is selected, the crew will see the advisory message, pack high flow, displayed on the CAS system. Finally, environmental system parameters can be monitored through the ECS page on the EICAS or MFD display. This page allows the flight crew to monitor values such as cabin temperature, cabin altitude, cabin rate of climb or descent, and other environmental system data. Together, the ECU, temperature controller, sensors, and distribution system ensure that the aircraft maintains a safe, controlled, and comfortable environment for both crew and passengers throughout all phases of flight. Rapid review. Learjet 40/45 air conditioning. The Learjet 40 and Learjet 45 air conditioning system uses engine bleed air or APU bleed air to supply conditioned air for the cockpit and passenger cabin. Bleed air first enters the system through the pack bi-level pressure regulating shutoff valve, which regulates the pressure of the air entering the environmental control unit. In normal operation, the system operates at approximately 18 pounds per square inch. When high flow mode is selected, pressure increases to approximately 26 pounds per square inch to improve cooling capacity. The environmental control unit, commonly called the pack, is located in the aircraft tail cone and performs the primary cooling function. The pack contains the air cycle machine, which consists of a compressor, turbine, and fan mounted on a common shaft. Bleed air is compressed, cooled in heat exchangers using ram air, and then expanded through the turbine to produce very cold air. This process is known as air cycle refrigeration. After cooling, the air passes through a water separator, which removes moisture before the air is distributed through the aircraft. The system provides dual zone temperature control, allowing the cockpit and passenger cabin temperatures to be controlled independently. Temperature control is managed by the Integrated Environmental Control System Temperature Controller, which receives inputs from cockpit temperature sensors, cabin temperature sensors, and duct temperature sensors. The controller modulates the temperature control valves, which regulate how much hot bleed air mixes with the cold air produced by the pack. In automatic mode, the controller maintains the selected temperature automatically. In manual mode, the temperature selectors directly command the temperature control valves. Low limit temperature protection prevents the system from producing excessively cold air that could cause ice formation in the water separator. If air temperature leaving the water separator drops below approximately 37 degrees Fahrenheit, the controller opens the low limit temperature control valve to mix warmer bleed air. The environmental control system also includes overtemperature protection. If pack discharge temperature exceeds approximately 450 degrees Fahrenheit, the crew receives a pack OVHT caution message. Duct temperature sensors monitor both cockpit and cabin air ducts. If duct temperature exceeds approximately 300 degrees Fahrenheit, the crew receives cockpit duct overheat or cabin duct overheat caution messages. Temperature limiters also provide additional protection by closing temperature control valves if duct temperature exceeds approximately 210 degrees Fahrenheit. The system also provides high flow mode, which increases airflow through the pack and improves cooling capacity. High flow mode increases bleed air extraction from the engines and should normally remain off during takeoff, landing, anti-ice operation and at high altitude. If high flow mode is selected, the crew will see the pack high flow advisory message. Environmental system parameters can be monitored on the Environmental Control System page on the EICAS or multifunction display. Together, the Environmental Control Unit, Temperature Controller, Sensors, and Distribution System maintain a controlled and comfortable cabin environment throughout all phases of flight.